Good morning. In this section, we will study set operators. Two or more sets can be combined in many different ways. For instance, starting with the set of mathematics majors at your school and the set of computer science majors at your school, we can form the set of students who are mathematics majors or computer science majors. The set of students who are joint majors in mathematics and computer science, and the set of all students not majoring in mathematics, and so on. Definition 1. Let A and B be sets. The union of the sets A and B denoted by A union B is the set that contains those elements that are either in A or B, or both. Note that the union operator is similar to the AND operator in the conjunction operator in when we have propositions, but not the same. This is an example of types. The union operator is applied to sets, and the AND operator is applied to propositions. By an element X belongs to the union of the sets A and B if and only if X belongs to A or X belongs to B. This tells us that A union B is the set X where X is an element of A or X is an element of B. The Venn diagram below shows the union of two sets A and B. The area that represents A union B is the shaded area within either circle represented A or the circle represented B. Example 1. Find the union of the sets 1, 3, 5 and 1, 2, 3. Solution. A union B is 1, 3, 5 union 1, 2, 3, and the union is 1, 2, 3, and 5. Definition 2. Let A and B be sets. The intersection of sets A and B denoted by A intersection B is the set that contains those elements that are in both A and B. An element X belongs to the intersection of sets A and B if and only if X belongs to A and X belongs to B. This tells us that the intersection of A and B is the set X where X is an element of A and X is an element of B. The Venn diagram on the following page represents the intersection of two sets A and B. The area represents A intersection B is the shaded area within either circle representing A or the circle representing B. Example 3. Find the intersection of the sets 1, 3, 5 and 1, 2, 3. Solution. The intersection of A and B is the set that contains 1 and 3. Example 4. The intersection of all computer science majors at your school and the set of mathematics majors is the set of all students whose joint majors in mathematics and computer science. Definition 3. Two sets are called disjoint if their intersection is the empty set. Let A be 1, 3, 5, 7, and 9, and B be 2, 4, 6, 8, 10. Classify the intersection of the two sets. Because the intersection is the empty set, the two sets are disjoint. Definition 4. Let A and B be sets. The difference of A and B denoted A minus B is the set containing those elements that are in A but not in B. The difference of A and B is also called the complement of B with respect to A. An element X belongs to the difference of A and B if and only if X belongs to A and X is not an element of B. A minus B is equal to X where X is an element of A and X is not an element of B. The Venn diagram below represents the difference of the two sets A and B. The shaded area inside the circle that represents A and outside the circle that represents B is the area that represents the difference of A minus B. Example 6. Let A be 1, 3, 5 and B be 1, 2, 3. Find A minus B. Solution. A minus B is 5. So the way we constructed this is we went to A and we looked at the first element, 1. We asked ourselves, was it in B? Yes. Then take it from the difference. We looked at the next element, 3. We looked at it in B and we tried to find B. We tried to find 3 in set B. Was it there? Yes. So subtract it from the difference. We looked at 5, the last element in set A, and we looked for it in B and we did not find it, so it was included in the difference. Example 7. The difference of computer science majors at your school and the set of mathematics majors at your school is the set of all computer science majors at your school who are not also mathematics majors. Definition 5. Let U be the universal set, the complement of the set A, denoted by A with a hat or vertical or a horizontal bar over it, is the complement of A with respect to U. In other words, the complement of the set A is U minus A. An element belongs to the complement of A if and only if X is not an element of A. This tells us that the complement of A is the set X, where X is an element of the universal set and X is not an element of A. In figure 4, the shaded area outside the circle representing A is the area representing the complement of A. Example 8. Let A be A, E, I, O, and U, where the universal set is the set of the letters of the English alphabet. Then the complement of A is the consonants B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, and Z. Example 9. Let A be the set of positive integers greater than 10 with the universal set of all integers. Then the complement of A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Corollary 1. A minus B is A intersect B, the complement of B. By definition, A minus B is the set X, where X is an element of A and X not an element of B. By definition, A intersect B, the complement of B, is the set X, where X is an element of A and X not an element of B. Since both sides of the equality have the same definition, the expressions are equal. Here are a few set identities. We have the identity laws, where the union of where A with the union of the empty set is A itself, and A intersection with the universal set is A. We have the domination laws. A union the universal set is equal to universal set, and A intersect the empty set is the empty set. We have the idempotent laws. The union of A with itself is A. The intersection of A with itself is A. The complement of the complement is A itself. We have the commutative laws. We have A union B is equal to B union A, and A intersect B is equal to B intersect A. We have the associative laws. A union the quantity B union C is equal to the quantity A union B union C. And A intersect the quantity B intersection C is equal to the quantity A intersection B intersection C. We have the distributive laws. A intersection the quantity B union C is A intersection B union A intersection C. A union the quantity B intersection C is A union B intersection the quantity A union C. We have De Morgan's laws. The complement of the union is the intersection of the complements. The complement of the intersection is the union of the complements. Let me say the first one again. The complement of the union is the intersection of the complements. We have the absorptions laws. A union, the quantity A intersection B is A. and A intersection the quantity A union B is A. We have the complement laws. The union of A and its complement is the universal set, and the intersection of A and its complement is the empty set. Example 10. Prove that the complement of the intersection of A and B is equal to the union of the complements of A and B. Solution: we will prove that the two sets A intersection B, that the complement of, looks like I don't have this here, so that the complement of the intersection and the union of the complements are equal by showing that each set is a subset of each other. First, we will show that the complement of the intersection is a subset of the union of the complements of A and B. We do this by showing that if X is in the complement of the intersection, then it must also be in the complement of A union the complement of B. Suppose that X is an element of the complement of the intersection. By definition of complement, X is not an element of the intersection of A and B. Using the definition of the intersection, we see that not X is an element of A and X is an element of B is true. By applying De Morgan's law for propositions, we see that we have not X is an element of A or not X element of B is true. Using the definition of negation of the propositions, we find X not an element of A or X not an element of B. Using the definition of a complement set, we see that X is an element of the complement of A or X is an element of the complement of B. Finally, by definition of union, we have X is an element of the complement of A union the complement of B. This shows that the complement of the intersection is a subset of the union of the complements. Next, we will show the reverse, that the union of the complements is a subset of the complement of the intersection. We do this by showing that if X is in the complement of the union, then it must also be in the complement of the intersection. And we use very much the same kind of logic as we did in the first project, in the first part of the proof. And we arrive at this final statement because we have shown that the complement of the union is a subset of that the union of the complements is a subset of the complement of the intersection, and the reverse, which I unfortunately don't have here, we can conclude that the two sets are equal.